Alright, for this lesson what we're going to do is we're going to start to combine um, the different gas laws we looked at, most notably Boyle's and Charles' law, and then take a look at Avogadro's law and start putting together what we know about gases and start to prepare ourselves to determine what happens during chemical reactions with gases and how the idea of the mole actually came about. What we're going to look at first is combining the gas law. In this case, we're going to combine the two laws, Boyle's and Charles' law, which gives us a relationship, as we can see here, between pressure, volume, and temperature. So if we have a gas at a constant amount of gas where we're not adding or taking any gas away in a system, and we change, say, one or two of the variables of that system, we can determine the third variable. So now we can start to look at what might happen to a gas if we make some changes along the way and alter that system. So let's take a look at some problems where we have to use this relationship. The first one here, we've got a small balloon. It contains 275 mils of helium gas, and we have a temperature of 25 degrees Celsius and a pressure of 350 kilopascals. We want to determine what the volume would be if we changed the temperature, dropped the temperature to 10 degrees Celsius, and then altered the pressure of the system as well. So we always start with what we know first. So I always like to write down what information was given to me. So my initial pressure is 350 kPa. My initial volume is 275 milliliters. Now we don't have to change it to liters or anything like that, so don't worry. And my initial temperature is 25 degrees Celsius. Now, what we'll have to do is convert this temperature to Kelvin right off the bat. So we'll add 273, 25 plus 273, and that's going to give us 298 Kelvin. Now, what else do we know? Well, we know our final temperature is 10 degrees Celsius. Again, we're going to convert that to Kelvin. And we know our final pressure is 101 kPa. So what we're looking for here is our final volume. V2 is our unknown. So let's take a look at what our relationship is. When I do these questions, I personally like to rearrange the formulas before I start substituting in. You could do it the other way. You could substitute everything in, then rearrange. It's all up to you, and you should get the exact same answer no matter what you do, as long as you don't break any math laws. So what are we trying to identify here? Well, we're trying to get V2 by itself. So in order to get V2 by itself, I'm going to have to cross divide my P2 down and cross multiply my T2 up. I like to use little arrows here to show what I'm doing instead of writing everything out in long. I'm sure the math teachers don't like that. But as long as you have arrows and you're following the math rules, you know, if it's on top, you gotta bring it to the bottom. If it's on the bottom, you gotta bring it to the top. So I get my final equation is going to be V2 is equal to P1 V1 T2 divided by T1 P2. Alright, looking pretty crazy. We got 5 variables in play. So now let's substitute our values in, and do the calculations. Then we're done. The only thing here is make sure you substitute everything in correctly. So 350 kPa. Always put your units in, even though it is going to take up a lot of room. Our volume, 275 milliliters. That's our initial one. Our final temperature, T2 is 283 Kelvin. Remember, it's not degrees Kelvin, it's just Kelvin. And divide that by T1 times P2. Well, T1 is 298 Kelvin times our P2, which was 101 kPa. And we get our final answer. And of course, our kelvins cancel out, our kPa's cancel out, and your unit that you should be left with, of course, is milliliters. And we get 910 milliliters. Now, in the last the last lessons, what I did was I explained how it's important to try and predict what's going to happen. Now, in this case, when we use the combined gas law, that gets more and more difficult to predict what we think is going to happen. And so, because of that, you can sort of make an educated guess. We notice that the temperature dropped and our pressure dropped. So if temperature drops and pressure drops, they could even themselves out. It all depends on how much the temperature drops versus how much the pressure drops. So anyways, for this it's a lot trickier when you're doing combined gas law to make your predictions. We've got another problem here. We've got a sample of argon gas. It occupies a volume of 2 liters at minus 35 degrees Celsius and 0.5 atmospheres. The question asks, what would its Celsius temperature be at 2.5 atmospheres if its volume was decreased to 1.5 liters? So again, we're going to write out everything we know. So let's start off with our initial pressure. So initial pressure was 0.5 atm. The reason why I go P1 first, P1, V1, T1, is because that sort of reinforces the what the formula looks like. But the order does not matter. Our initial volume is 2.0 liters, and our initial temperature, T1, is minus 35 degrees Celsius. Now again, we need to convert that to Kelvin, so minus 35 plus 273. And that's going to give us 238 Kelvin. Just pull everything down here a wee bit. Now we have what happens afterwards. So we, our final pressure, P2, is 2.5 atm. So our pressure is going up by a factor of 5. And the volume is being decreased by 25%, and we want to find T2. So again, we set up our relationship, P1 V1 over T1 is equal to P2 V2 over T2. Now in this case, I want to find my final temperature. So what I'm going to do here is I'm going to take my final temperature and I'm going to bring it up there, and I'm going to take everything in this box right here and I'm going to swap it down the other way. And I also want to get this T1 on the other side, so I'm going to take that. Oh my goodness, look how crazy it's getting. Follow the arrows. Anyways, So what I'm going to end up with is T2, brought that up from the bottom, is going to be equal to P2V2, all right, and the T1 gets brought up to that, divided by P1V1. Okay, again, 5 variables, everything rearranged. Hope we got right. Pretty sure we did. So let's substitute everything in. So 2.5 ATM multiplied by my final volume, 1.5 liters, times my initial temperature, 238 Kelvin. Divide all that by my initial pressure, 0.5 ATM, times my initial volume, which is 2.0 liters. Okay, now the fun part comes. Bust out the calculator and see what we get. 2.5 times 1.5 times 238. And we're going to divide that by 0.5 times 2.0. And we get 892.5 Kelvin. Okay, so the final temperature, though, they said they want it in degrees Celsius. So T2 is going to be 892.5 minus 273. Remember, whenever we convert to Kelvin, we always subtract. We always subtract our the 273 to go from Kelvin to degrees Celsius. And we get 619.5 degrees Celsius. So we can see that the temperature jumped up massively by increasing the pressure and decreasing the volume. Both things we know would increase the temperature by a great amount. So there we go. And this concludes the lesson on combining gas laws. You can take a look at the next section where we take a look at combining gases and starting to take a look at the reactions between combining gases and Avogadro's law.